Hello everyone, I am Dr. B. Ravikumar, Associate Professor, Department of ECE, Institute of Aeronautical Engineering. In this lecture, I am going to explain about multi-level NAND NOR implementation. So far we discussed about, in this regard, logic gates and what are the basic gates and universal gates. In the previous lecture, the basic gates like AND, OR, inverter are NOT gate, and universal gates are NAND, NOR. And why they are called universal gates? Since these gates, NAND and NOR gates, are used to implement any other gates, basic gates. Not only basic gates, we can also implement all combinational circuits and sequential circuits. So when we see those simple conversion from NAND to NOR, NAND and NOR into AND or inverter, they are like two-level gates. Now we will see that multi-level NAND and NOR implementations, any combination circuits can be implemented by NAND and NOR circuit. The combinational circuits are frequently constructed with NAND and NOR gates because these NAND and NOR gates are readily available in integrated circuits. Because of this prominence, we can prefer these NAND and NOR gates to implement any Boolean functions or combinational circuits or simply basic circuits. So it is required to study about the relationship between AND and OR and NAND or NOR. Once we know the relation between those universal gates to normal gates, so then we can easily implement whatever the Boolean function which is represented in AND or inverter and then implemented into NAND and NOR. So because of this NAND and NOR are universal gates, as it's shown in the figure, so we can convert this NAND and NOR gates into NOT gate and AND gate, OR gate as shown in the figure. Simply it requires one NAND gate to get a NOT operation. So A is given to the NAND gate, you will get A bar. So it is simple, combining two input NAND gate can be into one input which is given to A, and then you will get at output A bar. Similarly, you need to get AND gate by giving two NAND gates. One of the first NAND gate output is AB bar. Again, then giving to inverter, you will get AB bar bar. Then it will give the AB. Similarly, you get OR gates by combining three NAND gates. So one input is two inputs like complementary inputs achieved by using two simple single NAND gates, and these complementary input given to two input NAND gate, you will get A bar B bar whole bar, which is equal to A plus B according to De Morgan's law. Now the procedure to obtain the multi-level NAND gates. Suppose we were given by a Boolean function and then we need to draw the NAND and NOR logic. It is required that first to draw the logic diagram with AND OR inverter gates. And here it is assumed that the normal and complemented variables are available. If you whatever the variables exist in the expression which are either in complemented or normal or uncomplemented or both. So next, once we draw the logic diagram using this AOI model, AOI gates, then convert all AND gates to NAND gate with the AND inverter graphic symbol, AND inverter graphic symbol like this one. This is AND inverter graphic symbol, and then wherever the OR gates in the Boolean function or diagram, logic diagram, that OR gates converted into NAND gate with the invert OR graphic symbol as shown in this figure. So this is bubbled OR gate. Then third step, we need to check all small circles in the diagram. If for every small circle that is not compensated by another small circle along the same line, insert an inverter or complement the input variable. If we are connecting an AND gate followed by some other bubble in OR gate, this in the same line we will come across these two bubbles. Other than this case, we can provide at a primary input we can provide complemented input, or at a primary output we can provide another one input NAND gate inverter. Let us see one by one. By following these steps, we can convert a Boolean function into diagrammatic AOI form and then converted into multi-level NAND gate. Suppose a Boolean function is given by a plus b bar plus c, d bar plus be bar. So with the help of AND or inverter gates, we can draw this diagram. It is as usual. We know that how to draw the diagram. We can follow the Boolean functions and the logic gate equations. Wherever the product term, it is represented as in logic gate is AND gate. Wherever the sum symbol, like sum of product, we can represent it as OR gate. So it is look like a first variable a plus b bar plus c into d bar plus be. That means wherever the plus is there, it is represented as OR gate. Plus is there OR gate. And then wherever the multiplied dot is there, dot or simply multiplication, we can use the AND gate. So by drawing this one, so let us see first here. Take this one term, each term, d bar plus be bar. In the d bar plus be bar, we have a be bar nothing but one of the AND gate, and then add with d bar. D bar is the complemented variable and e bar is the complemented variable here. So in this case, we can take the first AND gate, draw this AND gate B. We can take B and D. And then this B and E we can add with D bar. I'm taking direct variable D bar. Sorry, it is OR gate. We can add. We can take OR gate. And this OR gate, this is one expression in the parenthesis, and then another expression B bar plus C. So this B bar plus C is nothing but simply OR gate. B bar is this is the OR operation. So it is the first level. So we can take the OR operation between B bar and C. B bar one input and C is the another input. Here it is D bar, and here it is B and E bar. E bar. Then we can B bar. We have now B bar plus C. These together to be ANDed. So this together, this output of this first parenthesis and this one is ANDed. So as we ANDed these two, we can take the AND gate, and then this entire two parentheses will add with the A variable. So take the direct A variable. We can take the direct A variable, and then we can OR with this consecutive output. OR with the output. This is called a Boolean function, logic diagram using AND OR inverter. So we have complemented variables which is represented by simple NOT gate, B bar for example, E bar. So we need a NOT gate, and here it is an OR gate, here it is OR gate, and here it is AND gate. This kind of symbol we can use AND gate. So 3 OR gates and 2 AND gates and 3 complemented variables means NOT gates. This is the AY diagram. In this diagram, first we draw this diagram for the given Boolean function, and then by following those steps, the next point is convert all AND gates to NAND gate with AND invert OR gate into OR invert. So wherever the AND gate is there, in the second point, the AND gate to NAND gates. So take that condition, we can take convert AND gates into NAND gates. So here it is, for the first is here it is one AND gate. So we can replace with this AND gate with AND with bubble, AND with inverter, and here it is now OR gate, bubble with OR gate, like invert OR gate. Now the same diagram when we see this here, so the first diagram we can take, here it is, actually it is AND gate, so we replace that AND gate into a AND gate into AND with the bubble, nothing but NAND. This is called B and E bar, and then D, it is actually OR gate, so we can replace that OR gate is with a bubbled OR gate, bubbled OR gate, this OR gate. Next here it is OR gate already, so this OR gate also bubbled OR gate. We can take bubble OR gate, and this output is multiply 100 with this output, but here we can use that AND gate as a NAND gate, AND bubble, and finally it is OR gate, so it is OR gate, so we can convert that OR gate into bubbled OR gate, that A variable with the bubbled OR gate, bubbled OR gate. If I am taking the numbers here, for example, OR gate AND gate 1, OR gate 2, AND gate 2, OR gate 3, here it is AND gate 1, OR gate 1. So OR gate 1, OR gate 2, OR gate 3 are converted into bubbled OR gates 1, 2, 3, and AND gate 1, AND gate 2 can be converted into AND with bubble, AND with bubble. Okay. So the variables here, we can follow the last step. Check all these small circles in the diagram. Wherever the small circle, yes, if it is a small circle here it is a small circle. This small circle in the same line, in this line there is no another small circle to get the A only. So that's why I am taking here, instead of taking A, I am taking now changing the variable is A bar according to last step. So actually that input is A, but in this on the same line I can replace this line with the bubble R. So in order to compensate that bubble, we can provide A bar. And then here also, actually there is no bubble in previous diagram, AY diagram. So here it is comes bubble, bubble comes. So we can change that variable is B bar, like actual variable is B bar C. Now it is B and C bar, B C bar. But here there is no bubble, so B bar as usual, it comes as usual B bar. and here a bubble is there. In previous diagram, direct D bar is given to the OR gate, but I am putting bubble, so that variable changed to this variable changed to like D bar to D. So I am changing the variable like this. So because of this bubble, this A becomes A bar. Because of these bubbles, B bar becomes B, C becomes C bar, and because of this bubble, this D bar. So here in this case, here already one bubble is there. The same line, one more bubble is there. So we can compensate with those bubbles. So that's why B and E bar won't change. So this is the one way first step, first we need to convert logic diagram and then logic diagram into bubbled R and bubble diagrams. So that nothing but a diagram with two symbols. We can use two symbols. Use two symbols. So the same diagram again we need to convert. Say entire diagram which converted to NAND gate only. As we can see here, this diagram, a bubbled OR gate, two input bubbled OR gate, which is equal to AND with bubble. So because A B whole bar is equal to A bar plus B bar. So here it is A is given because of bubble A bar, B is given because of bubble B bar. In R with R operation, A bar plus B bar, which is equal to A B bar is equal to A bar B bar. So AND bubble is equal to bubbled OR gate. So wherever the R bubble diagram in the diagram, we can replace that bubbled R into NAND gate, so that entire diagram will become converted into multi-level NAND gate. So in this diagram, we can replace this diagram this is the diagram which I drawn previous. Now replace this one. Replace this diagram, bubbled arrow, bubbled arrow. So when we replace that diagram into bubbled R into bubble NAND bubble, then that entire diagram becomes this one, A bar, bubbled R becomes NAND, and here also we can take bubbled R, nothing but NAND, gate. Already here it is NAND gate, so that NAND gate won't change. This bubbled OR gate can be replaced with an AND gate. And last one is already bubbled NAND gate. So this E bar, B, D, and C bar, B, A bar. So the entire diagram becomes NAND gate only. NAND gate 1, 2, 3, 4, 5. So this is nothing but multi-level NAND gate. Multi-level NAND implementation. It's very simple. Take the Boolean function and its corresponding AY diagram by using the AND OR inverter, and wherever the AND OR gate bubbled R, wherever the NAND gate NAND bubble, replace the OR gate with the bubble R, replace the AND with bubble NAND gate, and then wherever the bubbled OR gate replaced with the NAND gate, so that the entire diagram becomes NAND gate. But the Boolean function the functionality of the Boolean function using entire diagram into NAND gate. So it gives the same functionality. But using the final diagram, using this all gates are in NAND, such that whenever take any IC, the IC consists of 8 NAND gates, for example. So here it is 8 NAND gates. 8 NAND gates, like 8 NAND gates. So by using this IC, we can take this Boolean function by connecting logically of all NAND gates, so that we have readily available of these NAND gate chips and OR gate chips. So when we implement any Boolean function, we can take simple IC, we can implement that Boolean functions. If you require more than NAND gates that IC had, we can use another IC, we can connecting them both of those chips, and we can connect the Boolean function. That is the main advantage of this implementation of NAND and NOR, so that the diagrams, the similarity of those AND gates will be easily implemented using integrated chips. Let us see now. Sometimes we can also diagram, the given diagram is NAND gate, we can convert it into AOI. So before that, again we can see this one more example. Here in this example, the f is equal to Boolean function f is equal to cd plus e and a plus b bar. Cd plus e, a plus b bar. If you see this diagram, in this diagram, if you take that two product terms, like cd plus e one brace and a plus b bar another one. Let us see to draw this one in using AND OR inverter implementation. So CD is a AND operation. We can take the AND gate, and this AND gate output OR with E variable E. So this is nothing but C, this is D, and this is E. This AND gate output is CD. This OR gate output is CD plus E. This is one brace, and another one is A plus B bar. We can take A input and B bar input and OR gate. Take the A and B bar and OR operation. A input, B bar input. This OR operation is again ANDed with this above diagram. You will get F output. So this is the AOI diagram. AOI diagram. And OR inverter diagram. In this diagram, we can use two AND gates, two OR gates to get this Boolean function. Now, how to convert? How to convert NAND, multi-level NAND inverter? How to convert NAND implementation? By following those procedures, first draw the diagram. We just done this diagram, AOI diagram, and then replace the AND gates with AND with bubble, and replace the OR gate with the bubbled OR gate. So replace that diagram. I am replacing now. Just I am replacing with the AND gates. So here, if I am using this AND gates with AND with bubble, AND with bubble, and then OR gates replace with bubble with OR. So we can take the bubble with OR gate, bubble with OR gate, and then this OR gate bubble with OR gate. This output is going forward and then ANDed with this one. This AND get replaced with the bubble. When we see here, the first AND gate is replaced with the AND with the bubble. The second AND gate with the AND with the bubble. And first OR gate replaced with the bubbled OR gate. Second OR gate replaced with the bubbled OR gate. In this case, when we change this AND with the bubble for the first AND gate, and in the same line, another bubble is there in the second OR gate 2. This OR gate 2. So, these two bubbles are replaced with the compensation. And this second input of the second OR gate bubble is there. One single bubble is there. So, entire line, this entire line, one single bubble, so that the variable changes. Earlier it is E, now we can call it as E bar. Earlier it is C, now it is also C because no bubble is there. Earlier D, so now it is also D. And first OR gate, here in this first OR gate we can change with bubbled OR gate. So the names are changes, A bar here and B here. And this last AND gate, it is actually transformed to the second AND gate, second bubble AND bubble. But because of this bubble, wherever I am changing that second AND gate to NAND gate, to compensate this bubble, there is no bubble at the output. So that's why I am taking another NAND gate. To the NAND gate means it's like a simple bubble. So single input NAND gate I am taking to compensate that bubble. We will get a final output. So here, finally now we can replace this diagram, this first diagram, and this is NAND implementation using two symbols. And finally we can use only one symbol. We can use one symbol by replacing the OR with bubble into simple NAND gate. Then we can draw this diagram. So this is transformed into first one and NAND. First it is a NAND gate, so no need to change that NAND gate. And then this bubble OR gate can be changed into NAND gate because it is equivalent to NAND gate. Bubbled OR gate nothing but equivalent OR gate. So take the variable as it is. This one is C, this one is D, this one is E bar, and then A bar and B taken as a NAND gate because replaced with this bubbled OR gate into NAND gate because which is equal to NAND gate, and this output is connected to NAND gate, NAND output, and this is followed by another single input NAND gate to get the final output. So when we check this expression using the De Morgan's theorem by applying the output of this one is C D bar, and this one is nothing but C D bar into E bar whole bar, and this one is A bar B whole bar, and this one is an AND operation of these two expressions, C D whole bar E bar whole bar dot A bar B whole bar, again this whole bar, the output of this whole, because of this output this complement. So these two complements are cancelled. So what are the remaining, sir? The remaining expression is CD bar E bar whole bar into A bar B. So when we expand this one, CD bar plus E bar whole bar. So we can take the CD bar is as a X, E bar is a Y, X dot Y whole bar means X bar plus Y bar into A bar B, take parenthesis. So again inside C double bar cancel, you can take C plus D plus E A bar B. So here it is not C plus D. So this double bar cancel, we will get CD only. CD plus E, this double bar cancel. And then A bar A, here it is actually A bar B whole bar, that can be represented with De Morgan's theorem A bar plus B. This term using De Morgan's A bar plus B bar. A double bar means A only, A plus B bar. So we can get that A plus B bar. This is exactly equal to this function. So the NAND implementation and the Boolean function is same. That means that Boolean function represented in UNDAR inverter can be represented in NAND, which is same. But with the help of NAND implementation, it is very easy to manufacture, very easy to get the circuit using ICs. Then transform to UNDAR inverter. If we have a NAND gate implementation circuit, sometimes if you want to require that NAND implementation into UNDAR, the one way, there are two ways to represent this UNDAR. One way is by using Boolean De Morgan's expression. Take the the Boolean expression for this NAND diagram, and then each NAND diagram can be converted into UNDAR using the De Morgan's theorem. Another way is the second way to represent this NAND gate into UNDAR. Simply we can follow the each level. Actually, it is a multi-level. It is a level 1, level 2, level 3, level 4. 4-level NAND gate implementation it is. So in this level, alternative level can be converted into bubbled OR gate. That NAND gate converted into bubbled OR gate. So now I am converted this diagram into a bubbled OR gate. Bubbled OR gate. And this diagram into a bubbled OR gate. When I am converted this alternative gates into bubbled OR gate, and then whenever I am changing this NAND gate into bubble, so here it is one bubble, so this variable is converted into B. B bar can be converted into B, and remaining all are same. So then this diagram, wherever the two bubbles are coming, that means they are cancelled to each other. So they replace this diagram into C, D. It is these two bubbles are cancelled, so we can take that AND gate, and this B with OR gate. So two bubbles are like so I am replace this I am replacing this B complement and bubble. We can take term B. So I am taking this simple OR gate, and this A term and with this one. A term and, because why I am taking AND means this bubble cancel. So we can take the OR gate in the last. So what about this bubble? This bubble cancel. So we can take direct AND gate here and then connect to this OR gate, so that you will get AND OR only. A, B, C bar. So with this diagram we can use 1, 2, 3 AND gates, 1 2 OR gates. So it is like a here bar, nothing but complement, nothing but AND OR inverter. So we can also find out convert a NAND gate into AND OR simply by changing the alternative NAND gates into alternative level NAND gates into bubbled OR gate, and then those bubbled NAND gate output and bubbled OR gate can be cancelled, and then we can convert to OR gate only. So finally this diagram into AND OR diagram. And then the second way of approach to convert this multi-level gate is multi-level NOR gate. So not only we can convert this AND OR inverter into NAND gates, so we have also readily available of this NOR gates. So NOR gate ICs are also available. So the Boolean functions and combination circuits can be converted into this universal gate like NOR gate. In previous lecture we studied about how to convert NOR gate into basic gates. If you want to convert NOT gate A bar, just keeping single two inputs are combined together and giving to the NOR gate, you will get A bar NOT gate. And one NOT gate output is followed by another one NOR gate is followed by another NOR gate, will get OR gate, because first output of the NOR gate is A plus B whole bar, that can be passing through another inverted NOR gate, will get A plus B only. And same NOR gate using, we can implement AND gate, we can use 3 gates. So it is very easy to remember. When we want to implement universal gate NAND to AND, require only 2 gates, because it is NAND nothing but AND plus bubble, AND plus NOT, so it requires 2. But OR you will require 3. Similarly, in the NOR implementation, NOR require 2 gates for OR, because it is from NOR is nothing but from OR only. But to implement AND, it requires 3. Then what are the steps to follow to implement NOR implementation, multi-level NOR implementation? Same way, whatever the Boolean function is given can be first done with the AOI diagram, and followed by convert all OR gates into NOR gate with the OR inverter. So in order to convert OR to NOR, first with the help of OR inverter, OR gate with inverter symbol, like it is OR with the inverter symbol, and then convert AND gates, all AND gates into NOR gate with the help of invert AND symbol. Here in this, just replace that invert AND symbol, and check all small circles is there wherever is there. The 2 circles are in the same line, left with the uncomplemented variable. If any line with a single variable, single circle, if it is primary input, take that primary input variable gets complemented, or if it is primary output, just take the another single input NOR gate. This is the diagram, and this is the Boolean function we can take here, AB plus E and C plus D. AB is the product term, plus E is the OR gate, and then C plus D is the OR gate. These two are together in ANDed with 100. So A plus AB, AB means it is AND gate, and this AND gate output is ORed with E variable, so we can OR gate with this output of AB. And another term we have C plus D, is OR gate, C and D terms are gets OR. This output of this C plus D is combined with AND with this entire brace, like AB plus C. So we can get this Boolean function here. Now this Boolean function is how to convert this into NOR implementation. As I said, wherever is the OR gate, that OR gate is replaced with the OR inverter. So OR inverter, AND gate is replaced with the bubbled AND gate. So if you convert this diagram into this NOR implementation, we can take AB like AB is simple. Sorry, AB with bubbled AND gate. Take the bubble for the AND gate, bubble AND gate, and this one is OR gate. So this OR gate is replaced with OR with bubble, like an OR gate. This OR gate also replaced with OR with bubble. So whenever there is no bubble, we can take as it is terms. And here it is bubble, like there is no bubble, we can take as it is. And here it is bubble comes, we can take bar, A bar and B bar. This one is connected to bubbled AND gate. You will get F. This is a two symbols. Two symbols. This diagram now converted into replace the wherever AND with bubble with AND replace with OR gate, which is equal to this diagram, which is equal to NOR gate, to input NOR gate. So replace that diagram. Take the A bar, B bar, replace that diagram with a simple NOR gate. NOR gate. And this is the input E. Already it is an OR gate. And below circuit is also already it is an OR gate. This NOR gate output is given. It is also which is equal to 2 input NOR gate. So that the entire diagram is into single one symbol, which is nothing but bubble, like an OR gate. The symbol is called OR with the bubble. So 1, 2, 3, 4 NOR gates are required to implement AB plus C plus C D. So entire NOR gates we can implement it. So any chip IC which has 4 NOR gates, just we can call 4 among them, we can connect it according to logic diagram. Then we can implement this Boolean function using simple IC, one IC. Here also it is possible to convert from this diagram into AY diagram. So what is the diagram? For example, it is a NOR diagram, another NOR diagram, NOR gate. Take the NOR gate. We can take the NOR gate. This is actual input diagram. A bar, B bar. E, C, D. This diagram into transform into AY diagram. How to convert this AY diagram? This is level 1, this is level 2, this is level 3. So alternative level can be converted into this NOR gate can be converted into bubbled AND gate. So first level NOR gate, and then in the second level we can convert it a bubble AND gate. This is the second input, and this one is NOR gate. First level it is as it is, take as it is. On third level also take as it is. So what happened here, it is this bubble cancel, A bar, B bar. So when I am using this bubble here, that variable is changed to E bar, and here it is C and D. This bubble, so this is no, here it is. Bubble. So in this case, we can take for this expression we can take this is the second level. So we can actually take the like a multi-level diagram, we can convert it to this one. So it is not possible to convert this bubble to uncomplemented one. So in this we'll see in the next class. In this lecture, whatever the given Boolean function, we need to convert a multi-level NAND and NOR implementation. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.